All right, I'm Dat Nguyen. I'm the project manager of the Human Powered Airplane project. This is Stephen Wu, and this is Samuel Reyes, those team leaders on the project as well. We're here today to give you a brief overview of the Human Powered Airplane project and what we've been doing the past few months. First, we'll go over the background of the human powered airplanes in general and our brief history. And then afterwards, we'll go into the work we've done in the past. And then we go into the actual subsystem presentations themselves, where we go over all the teams and what they each did. And then after that, we'll go over the budget, along with our documentation efforts. And then finally, we'll go into the innovations the project has made, as well as our plans for the future. I'll now hand this to Stephen Wu, who will talk about the history of the human powered airplanes.
Thank you, Mr. Nguyen. So as you can see, our project is a human powered airplane, and I just want to give you guys a brief timeline about all the major human powered airplanes that have been made since the 1900s. The first effort for a human powered airplane was made in 1921 in France, as you can see in the picture above. This plane design actually traveled around 13 yards while gaining about a meter in height. After this, the attempt in 1921 was the first attempt, and the next notable one was in 1960 by Sunpac, which traveled 75 yards. The most major accomplishment by a human-powered airplane so far was in 1998 from MIT's Daedalus, which traveled 71.5 miles in under 3 hours. This is just a brief timeline of just HPAs that have been done over, and I'm going to hand this over to Samuel Reyes, who's going to tell you about UC Irvine's involvement.
Thank you, Mr. Wu. As for UCI, there are two teams that built two HPAs back in 1987 and 1990, and it wasn't until recently that the HPA project got started back up again by UCI alumni Jacqueline Thomas, and now our goal is to fly the HPA by the end of summer of 2015. And then on to some specs at the plane. We have a wingspan of 108 feet, a wing chord of 4 feet, a propeller diameter of 12 feet, and a projected total flight weight of 300 pounds. And now I'm going to throw this off to Mr. Nguyen to talk about organization.
As you can see, the organization of the project is relatively centralized. At the top, there are the advisors along with the project leaders, such as the project managers and chief engineers. Our job is to make sure that the project is heading in the right direction, along with giving technical input to the team leaders whenever they require it. Below us are the team leaders themselves, like Steven and Sam, and their job is to make sure that all the parts in their subsystems get completed and get completed on time. And below them are the team members themselves. The team members are not locked into their respective teams. They can go to whichever team needs more work. So it's not a rigid system, it's more flexible in nature. Now, before I go into the actual subsystem presentations themselves, I'll need to give you some context as to what we did in the past few years. So last year, in 2013-2014 school year, we spent most of our time building spars and cutting out foam for the tail and for the wing. In the process, we also made a tail boom. And with all of our knowledge of building spars and tail booms, we built a fuselage frame, which you can see in the top left. And then over the summer of 2014, we built the tail and also the wing. You can see the wing there sitting in front of Engineering Gateway, which was for our load test to make sure that the wing was actually structurally sound. And it passed the load test very well, which surprised us, and we were very glad it didn't break or anything. So with the tail boom build, and the wing and the fuselage frame build, all the major structural components of the human powered airplane are complete. All we really needed to do these past quarters, was to do some finishing work. I'll now hand this off to Mr. Wu, who will talk about the wings.
Thank you, Mr. Nguyen. So after we proved that the structural members of the wing section were sound in terms of loading, we decided to protect these structural members by first applying foam leading edges, which not only act as sheeting, but help conform to that airfoil shape. After the leading edges will be attached, we were also doing research on wing skin, which provides a nice seal to our airfoil contour. Fall quarter, we did a lot of research in choosing the right wing skin material, which would be durable under different temperatures, as well as just its overall stretchability to wrap around each 25-foot section of the wing. And in the winter quarter, we decided to apply all the foam sheeting to all the wing sections. In fall quarter, when we applied the leading edges onto our center wing section, it took approximately about 4 weeks. And through a lot of optimization and just a better allocation of our manpower, we were able to lower the time to a time span of 3 days. Winter quarter, we also made a box to house all the prepared wing sections, and right now we are currently preparing our final wing section. I'm going to hand it off to Mr. Reyes, and he's going to talk about our controls.
Thank you, Mr. Wu. As for our last quarter, we went through various iterations for our tail fairing, but due to weight constraints, we decided to not add a tail fairing to our H-tail. And during the last couple of weeks of fall quarter, we successfully wing skinned the vertical tail sections of the H-tail. And then this quarter, we're testing the tail boom deflection to see how it would work during flight. And we're also testing the wire tension within the tail boom to see if it changes during tail boom deflection. Now I'm going to pass it off to Mr. Nguyen to talk about fuselage and propeller.
So for the fuselage, at the beginning of all quarter, we did some calculations to see where the center of gravity for our plane was. And we found out that it was a bit too far aft of the whole airplane. And so which meant that when the plane took off, it would likely nose up and roll and hit the ground, which would not be good at all. So we had to find out how to move the center of gravity of the airplane forward again. We could do that either by moving the wing back or moving the pilot forward. We decided that moving the pilot forward was the most advantageous because it was easiest to do. So we spent the rest of fall quarter and a bit of early winter finding out how far forward the pilot needed to move, and we got an answer about a couple weeks back. About 2 feet. About 2 feet is how much the pilot needed to move forward. But the fuselage frame was not made for the pilot to move that far forward, so we had to also extend the frame, which is what we're currently doing. And you can see me in the frame right there, seeing how far forward the pilot needed to move. For the propeller, last year, what we mainly focused on was refining the manufacturing process. After we got that down, we focused on building the actual propellers themselves, and so in fall quarter, we built all the components we needed to assemble the propellers. And then winter quarter, we seamed all the propellers together. You can see me there standing with one of our 6-foot propellers, which easily is more for me. And then to test the performance of our propellers, we use our test stand, our propeller test stand, and we pedaled really quickly and measured the thrust that we were able to produce. And we got about 50 pounds of thrust when the cart was moving at a few miles an hour, which told us that our propellers were made well, and also that the propeller hub configuration on our propeller test stand was also adequate enough to be used on our actual airplane. And that concludes our subsystem presentations. I will now hand this off to Mr. Wu, who will talk about our budget.
Thank you, Mr. Nguyen. So the current budget listed here is considering that we're optimizing all the materials we have in-house. Currently, the current budget is near $7,000, with most of the funding being directed towards the logistics for our first test flight. This involves us carrying all the pieces and making sure there's a secure cage to deliver all the completed sub-assembly parts for assembly. Now, the rest of the other parts of the budget are directed towards the completion of the actual sub-assembly parts and are just an approximation of what we might need to actually make sure all the sub-assemblies are completed. I'm now going to hand it off to Mr. Reyes, and he's going to about documentation.
Thank you, Mr. Wu. As for communication and documentation, it's still a bit of a work in progress. However, we are making strides by having the team leads meet 3 times a week so we can keep in constant communication about each section of the aircraft. As for past documentation, most of it can be found on our site, ucihpa.com. And currently, we're using PDMWorks as a document control so that team leads can go in, make necessary changes when needed. And now I'll pass it off to Mr. Nguyen to talk about innovation.
When we made the human-powered airplane and originally designed it, we didn't want to look like any other human-powered airplane because that would be really boring and there would be no point. So we decided to add a whole bunch of innovations to it, some of them better than others. Our most major innovation was that we found that a square spar was better than a circular spar in bending, but that almost all other human-powered airplanes that use a circular spar for some reason. Because square spars had never been used before, we decided to make a MATLAB program that predicted how much a square spar deflected given a certain layup and given a certain loading. And that code told us how we should make our layup schedule. And so we listened to that code and we built a spar and then we tested it and broke it. Then measured the deflection data. And after a couple trial and error runs, we got a curve that you can see in the bottom right, where our predicted deflection data almost exactly matched our actual data, which meant that our code was very accurate and therefore trustworthy. And we used that to build all of our spars. We also did not want any external wire cross-bracing because that would create more drag. So we decided to get rid of wire cross-bracing, which allowed us to make a wing-level fuselage design. And that also allowed us to make a fully cantilevered wing, like you can see in the silhouettes in the top left and top right. And it actually makes it look like an actual airplane rather than most other human-powered airplanes, which look like a set of wings and then a box underneath. And because our wing is on the same level as our fuselage, we needed some ground clearance, so we are also one of the only human-powered airplanes to have an H-tail. And now I'll pass this off to Mr. Wu, who will discuss our plans for the future.
All right. So the final plans for winter quarter and spring quarter for the wings team is actually to finish wing skinning all of our wing sections and making sure that a nice seal is placed across all 5 sections of the wing.
And by the beginning of summer, controls team will start to calibrate controls.
Yeah, our other goal is to complete our fuselage and make sure all the sub-assembly components can fit with the fuselage, including the drivetrain and the tail.
And finally, we will assemble and test fly the HPA at the end of summer of 2015.
And that concludes our presentation. Many thanks to everyone on our team